Previously, we have seen the flat fading, the assumption which give rise to flat fading, the envelope of the received signal, and the correlation of the received signal with itself, which is in the form of Bessel function. From there, we discussed coherence time, and from coherence time, we discussed whether this is slow fading or this is fast fading. And we said that the slow fading is usually preferred because we can easily recover the transmitted signal as the channel is almost constant throughout the symbol duration. But however, there is one problem with the slow fading. So now in communication system, we usually consider the received power at a distance t to be greater than or equal to gamma th, some threshold. And this is studied in order to have a better understanding of coverage probability, outage probability, and the BER if we want to calculate the bit error rate expression. And we say that if this received signal strength at distance d is greater than gamma th, we say we have a coverage. If this received signal strength at distance t is less than gamma th, we say there is no coverage. Now let's see what is the problem with slow fading. Let's say this is the threshold. If we consider the signal is fluctuating slowly, and if we consider even much slower fluctuation, and if we consider the signal is very slowly fluctuating. So what it means is the signal, the point at which the signal goes below the threshold, it takes a lot of time to come back above the threshold. So that means once the signal goes in outage, it remains in the outage for a very long duration of time, which is not with the case of fast fading, because in fast fading we had fast fluctuations. So it does not take much time to get out of the outage region. Now, since the signal is fluctuating, we can also capture the rate of fluctuations, and we know that the maximum rate of fluctuations can be captured by Fm is equal to V by C into Fc, which can be positive or negative. Positive if the vehicle is approaching towards the base station, and negative if the vehicle is going away from the base station. Also, when the signal is coming at the receiver with certain angle theta n, we can get the Doppler frequency along this path. And now this Doppler frequency is getting added to the carrier frequency. So what we get is Fc plus minus Fd, n. So this implies, in other words, we can say what transmitter sends is a signal at Fc, but the receiver perceives the signal to be coming at frequency Fc plus minus Fdn. And this is not problematic if we consider that the transmitter, there is only one path between the transmitter and the receiver. So in that case, the receiver can just tune its frequency to Fc plus minus Fd, n, depending whether it is going towards the base station or it is going away from the base station. But however, the problem comes when there are multiple paths. So in multiple paths, instead of considering a single frequency Fc plus minus Fdn, we have a whole set of frequencies within this range. So what we would like to do is we would like to see what is the weight of these frequencies, or which percentage of which frequency is present in the signal. Or in other words, we can also say what is the spectrum of fluctuations. So what we mean is, if there is fluctuations happening, we would like to see what is the frequency content of these fluctuations. And to calculate this, we cannot rely on the Fourier transform, because Fourier transform is based on the snapshot. And since this is a random process, at every time the fluctuations will be different. So the best way to characterize this is using the power spectral density. And this power spectral density is obtained by taking the Fourier transform of the autocorrelation function. And since we already have the Fourier transform since we already have the autocorrelation function, this is the most reliable method in our case. And this phi HH, we know that this phi HH of delta t is equal to phi HI of delta t. That is the baseband received signal. And if we try to find its power spectral density by taking its Fourier transform, what we are left with this expression, where this gives us the power spectral density of baseband signal. Now, if we try to look at its plot, so what we see is, when frequency is equal to Fm, if we put this F is equal to Fm in this expression, this term will cancel out and this will become 0. And in the end, we are left with spectrum power spectral density to be equal to infinite. So that is why we are achieving this infinite at the positive Fm and the negative Fm. And when F is equal to 0, if we substitute F is equal to 0 in this expression, this term will become unity and we are left with this quantity. So that means we have a certain minimal quantity that is present when F is equal to 0. And this spectrum is known as Jake's spectrum. Next, we can also compute the spectrum of the passband using this expression, where the spectrum of the passband is related to the spectrum of the baseband through frequency f minus fc and minus f minus fc. And if we solve this, we get this expression, which is quite similar to the previous expression, but the only difference is now f is equal to f minus fc in this case. And why this is so? Because we know that the passband signal is related to the baseband through a carrier frequency fc. And this whole discussion about Jake spectrum is valid when p of theta is equal to 1 over 2 pi. That means at a receiver, the probability of the rays coming from each direction is uniform. That is for the relay fading scenario. And there is no line of sight component or specular component in this case. However, if we consider there is some strong specular component present, then p theta would not be equal to 1 by 2. Instead, it would be equal to this expression, where theta naught is the angle of arrival of specular component k upon k plus 1 is the amount of power contained in this specular component. P hat theta is the continuous angle of arrival distribution, and 1 upon k plus 1 is the amount of power in the scattered component. And then if we would like to see the Jake spectrum when there is specular component, what we achieve is this, that at a frequency, particular frequency, there is a strong line of sight component. There is a strong line of sight component that is coming from an angle theta naught. And this spectrum is known as Jake spectrum plus strong specular component. And this is usually known as the Doppler spectrum. And why it is known as Doppler spectrum? Because the spectrum is usually considered because of the mobility that is present in the scenario. Because of the mobility, what we are getting is fd, n, and this fd, n gives rises to this spectrum.